Our speaker tonight is John Portune, W6NBC. John is a ham's ham, not afraid to touch the hardware and build stuff. And he's going to talk today about Cavity Duplexers, not just simple assembly or building it. He's going to talk about the physics of it, tuning, how it works. Without any further ado, I'm going to turn it over to John.
For any of you who are would like to and don't know about the book that I wrote nearly 20 years ago now on cavity duplexers and duplexers, there's the actual link to it. It's free to download. It's a PDF document on my website, w6nbc.com/articles/duplexer.pdf, or take a shot of the QR code down there at the right and it'll take you there. And you can see the book. It's been around for a long time and all over the internet, but it's from it that all of this is derived. Back when I was a hilltopper and building repeaters and building duplexers, because they were black magic to me then too, and I wanted to understand them. And in fact, this is a different presentation than most of the ones that I do. Most of the ones that I do are more DIYs or do-it-yourself or homebrew projects that you can actually go out and build. I don't think as many people are building duplexers anymore or cavity or repeaters anymore, although they're still out there. And this is a repeater hill here in my area called View Hill. You can see the repeater just under the Sea of the Cavities. Anyway, so this presentation is not so much a build it yourself. This is more of an FYI presentation to introduce you to a topic that, as it was said, that is somewhat of a black magic topic to an awful lot of hands. They know of this device, these things, but they really don't know much about them or what they do and what they are. So we're going to talk about cavities and cavity duplexers as used mainly in 2-meter and 440 repeaters. And of course, there are very few hams, I would guess, that don't know what an FM voice repeater is. You know, you're just a sampling of pictures of various 2-meter 440 repeaters, either on commercial hilltops or on tops of buildings or even in people's homes up on hills. And the one in the bottom middle is a repeater that we have locally here. As I was flying over one day, took a shot of it from the air. So FM voice repeaters are certainly something that the average ham is well aware of and uses extensively, even to this day. And but FM voice repeaters didn't exist for most of ham radio. They really only begin in 1950, and even then they were AM, not FM. And repeaters, 2-meter repeaters, have had a stellar growth over the years, basically really taking off in the 70s. But they began in the 50s, of course, with a few AM repeaters. But up to that time, ham radio was all an HF phenomenon. And there was 2 meters in use, but it was a kind of a specialist use and not much use made of it in the 50s. But by the time the 70s came along and I came back from living in the UK, I was just into the beginning of the 2-meter FM repeater explosion, which went for 20-some, 30-some years, 40 years actually, until it pretty much hit a peak in about 2010. Now it's interesting to think about where the FM voice repeater is going to go. I don't think it's going to go away, but it's destined to change as all of these new modes come about. So this explains the tapering off. But FM voice repeaters, as you can see from this curve, which is fairly accurate, we have 35,000 FM voice repeaters in the United States right now. How many there will be in another 10 years or another 20 years, that's hard to say. But for the moment, they're still there, and every one of them depends on a cavity duplexer. Well, here's the whole thing that leads to the duplexer. This is the sort of central ingredients of an FM voice repeater and other types of repeaters as well too, but principally the FM voice repeater, which we are all most familiar with. And it consists of basically these basic elements. Obviously, a transmitter and a repeater used to repeat your signal from your mobile or your handheld and send it back out over a wider range. We all know what a repeater does. But for most repeaters, it does it on a single antenna. Now, I know that there are some low-cost repeaters that may use two antennas to save money. But by and large, repeaters all use a single antenna to do it with. And there's, of course, some electronics which control it, called the controller, which is an interesting part of it. I enjoyed building controllers as well as building repeaters for many years. But this interface between the transmitter and the receiver's single antenna is the thing we're talking about tonight, because the information coming from the transmitter has to go into that antenna at the same time as the information coming back from you. In fact, the repeater has to transmit and receive at the same time. I know most people may understand this, but just to state it very succinctly, think about it. That repeater up on the hill, when it's repeating you, is talking and receiving at the same time into one antenna. And that's not a mean trick. It's a pretty difficult thing to accomplish. And because that transmitter, when you look at it from a power point of view, not a dB point of view, but a power point of view, the strength of the transmitter in watts compared to the signal coming in from your mobile antenna or your handy-talkie, which is down in microwatts, is 1,000 million times stronger in power. And that has to all happen at the same time on one antenna, with those two items, the transmitter and the receiver, hooked simultaneously to that single antenna. Like I say, that's not a main trick. And here's what it's accomplished with: a thing called a cavity duplexer. And there's a picture of a 4-cavity duplexer. It must take the signal coming off the antenna, and it also must be used to put the signal back on the antenna. And as you can see, the transmitter is hooked to one port of it, the receiver is hooked to another port of it, and the antenna is hooked to the middle port of it, which combines the two. So the received signal has to get to the receiver, and the transmitter signal has to get to the antenna, and these have to happen occasionally without those two signals interfering with each other. That's not an easy trick. So the duplexer's job, and it's a difficult job, is to keep those two signals separate. That 1,000 million times the power of the transmitter, with the weak little signal coming in from your mobile, have to be kept separate so that the two don't interfere with each other. Just to give you a little idea in numbers, sometimes the numbers are more easier to comprehend. Here's the number of watts that are coming out of the repeater at the bottom. Let's say it's a 100-watt repeater, which is probably typical of a lot of repeaters. Maybe some are less than that, but that's pretty typical. And there's your signal coming in on the same antenna, and it's that many watts. Look at all those zeros. If you turn that into volts instead of watts, it's still a big number. And as you can see, a 100-watt transmitter puts a 71-volt signal into that antenna, but your signal coming back is 0.22 microvolts coming in. Now, what's that column on the right? Well, that's what the professional radio men use to compare these two signals. They don't measure the difference between transmitters and receivers in watts so much, or in volts. They measure it in what's called dBm. And they all say the same thing. All three of these columns are identical. They mean the same thing, just a different way to represent them. dBm is a dB, a logarithmic scale based on 1 milliwatt into 50 ohms, which is a 0.22 volts into 50 ohms, 0 dBm. A transmitter is at 50 dBm positive. The receiver is working down at minus 120 dBm negative. That's a tremendous range. That's the dB reference. Well, here's what the duplexers look like. It's a sampling of of the hundreds of different kinds. There's a nice typical 2-meter one right in the middle. And everything here except the black ones are 2-meter repeaters, a couple of 4-cavity ones, some 6-cavity ones, and 2 UHF duplexers. Both of the UHF duplexers are 6-cavity or 6-bottle or 6-can duplexers. As you can see, and the one on the bottom look like a 10-can or a 10-bottle duplexer. So these are just some pictures of some typical duplexers. I've used duplexers that look like this, and of course, because I wrote the book and I'm talking about this, I've built duplexers because I got tired of this being a mystery. I wanted to find out about these things, these bottles that you used up at your repeater to make the thing work. How do they work? Okay, well, basically they're filters. We all know the term filters. Radio and electronics are filled with filters to get rid of some signals, to eliminate interference, or to pick out certain signals. Filters are a very common factor in electronics. And of course, a duplexer is just a complex bunch of filters. Now, filters, as in general, not just in duplexers, but in general, filters fall into 3 categories. This is pretty basic stuff. Like I say, this is kind of elementary talk, this lecture, sort of FYI talk, but it's important to emphasize these. Filters, including duplexers, fall into one of the filters in them, fall into one of 3 categories. High pass, low pass, and duplexers don't use high pass, low pass filters, except maybe in the preamps, but the duplexer itself does not use high pass, low pass. High pass filters are ones that let frequencies above a certain frequency go by and don't stop anything below it. Or in the case of the one you see down there on the left, the low pass filter, which lets everything below 48 megahertz pass. Well, that's not a filter that you're going to use in a repeater. The 2 at the bottom are the kinds of filters, although not in that form, the kinds of filters used in duplexers. Bandpass filters, or B sub P, BP filters, and BR filters, or band reject filters. And as you can see, these are a couple of inline filters, not for repeater use, but for other ones. The one on the left is an airband filter that you might find in the radio if you fly private airplanes, that might go in the transmission line of the 2-way radio in your airplane to filter out everything but what you want. So it's a bandpass filter. It filters passes the airband. And the one on the right is a notch filter, or what's called a suck out cavity, or a band reject. And it rejects everything from 88 to 108 megahertz. Anybody recognize those range? Yeah, that's the FM broadcast band. So maybe you've got a big FM transmitter, FM broadcast radio transmitter just down the street from you. It's getting into your 2-meter radio. So you might put one of those notch out filters or suck out filters in your receiver to get rid of the local FM station. So remember, repeaters are built out of the 2 lower kinds, band pass, band reject filters. Okay, and here's what they look like in graph form. The band pass filter, and they're both made out of the same things. They're both made out of cavities. We're going to get to cavities here in a minute, or bottles. But they have these characteristics. The band pass bottles, or the band pass cavities, have the characteristic you see on the left. They pass a fairly wide range of frequencies. Usually for the duplexer, they pass the band that you're running the duplexer in. As you can see here, this is a bandpass filter for a 2-meter duplexer centered on just below 147 megs. And at its peak, it has very little loss. As you can see, the insertion loss up there at the top, but it has a fairly wide bandwidth to pass pretty much the whole band. And this is typical of duplexers, whether for ham or commercial, and they just tune that bandpass to where they want it. They also use notch cavities, or band reject cavities. These are the real workhorses of duplexers because they have a very narrow bandwidth. They get rid of some very specific frequencies or a very narrow range, and they do it with high efficiency. You'll notice that the bandpass filter only has a typical skirts of about -6 dB, which is about 4 times in voltage. Only gets you down about 6 dB off of what it passes. But the notch filters often have a rejection of up to 30 dB, which is 10,000 times in voltage. So notch filters are the real workhorses of duplexers, although bandpass cavities are used too, as we will see. Both made out of the same material, big, round copper or aluminum tubes or bottles. Now, filters also come in 2 types, not just duplexer filters. We only use one in duplexer filter. They come in 2 types, active filters and passive filters. Now, I'm showing you an old-time radio of the 40s there. You might not think of an AM broadcast radio as a filter, but of course it's a filter. It's filtering out everything except the station you're listening to, because into its antenna come all the radio stations on the band. But that AM radio is filtering out everything except the one you want to listen to. So it's certainly it's actually a notch filter quite well. But it's an active filter. What do I mean? It takes power to run it. See the cord coming in the back? That's what an active filter is, a filter that requires power to run it. And most active filters are low-level filters or low-signal filters. But there's also passive filters. That one on the right is a filter. You all recognize it. It's a ferrite choke that you might clamp on the outside of your coax. What for? To get rid of or to filter out any current that's on the outside of your coax. But there's no power running that. It does it simply because of what it is. It's a passive filter. And that's the kind of filters that are used in duplexers. They're passive filters. Oh, why? Because only passive filters can handle the transmitter's power. You can't put 50 dB of power through a powered filter. You're going to burn it out. But you can put 50 dB of power or 100 watts through a passive filter, and it'll handle it just fine if you make it husky. And that's, of course, what the cavity filters are. They're husky filters. They're passive, heavy-duty, power-handling filters. Okay, here's what the filters are in a duplexer. For small signals, they're found all throughout the radio world. Most of them are built with little coils and little capacitors. And all filters essentially are some combination of coils and capacitors, whether they're actual coils and capacitors or virtual coils and capacitors, as they are in a cavity. They still are L and C. They still are inductive and capacitive reactants. But for the power cavities power filters that we use in duplexers, we have to resort to coaxial filters, heavy-duty, large diameter, husky coaxial filters, which are shorted lengths of transmission line. Many of you will know that if you take a piece of transmission line, it has inductance and capacitance, distributed inductance, and if you short the end, or if you leave it open for that matter, it forms an LC filter. A short piece of transmission line is a great filter. You may use them as field day to keep one of your transmitters out of another one. Well, coax makes great filters, especially if you make it large in diameter. And that's what duplexer filters are. They're big, large diameter, usually several inches in diameter, heavy metal pieces of coax that are a half wavelength long. And that's what you see there in the middle of this picture. That's a quarter wavelength open-ended cavity or open-ended piece of coax, shorted at one end, like the coax at the top, and open at the other end. And it forms a great filter, has very, very nice filtering action. It does that because of the electric and the magnetic fields in it. It's just a piece of transmission line, though, quarter of a wavelength long, shorted at one end, and open at the other. And that's how all the filters are inside of duplexers. They're all usually speaking, maybe 95% of them are coaxial pieces of transmission line, shorted at one end, open at the other, with the center conductor quarter of a wavelength long. That's how they work. All right. if we're going to use big, heavy-duty pieces of coax, quarter wavelength long, we've got to couple the energy in and out of them so we can use them as a filter. And here's how we do it in a cavity duplexer. There's the cavity there. It's a metal cylinder with one end closed and the other end open with its center conductor. It's just a piece of coax, but it's a great big piece of coax in diameter, typically 2, 3, 4 inches in diameter, sometimes even bigger than that. But to get the energy in and out of it, to get the filtering action of it, we've got to couple our energy into it. And then so that it will resonate. And then we put another loop in it to take the energy back out, all nice and filtered. That's how a cavity works. It's 2 loops going in, one coming out. One puts the energy in and one takes the energy out. And because it works on the magnetic field, which is circular around the center conductor there, the magnetic energy passes through the loop and couples in and couples out in this case. And this is probably 90% of most cavity duplexers used for FM voice repeaters are of this form right here. Large diameter bottles, quarter wavelength center conductor, shorted at one end, open at the other. And here's the coupling loops that out of a variety of 3 different kinds of duplexers or cavities. And you can see using different connectors, the one at the top with N connector on it, coming through the wall of the cavity, and BNCs at the bottom. This is common for ham duplexers. And there's some PL239s at the bottom, driving some nice big coupling loops in some kind of big cavities. Also, though, we can couple into a cavity a different way, by what's called probes. There's also an electric field inside that length of cavity, which runs the length. The magnetic field runs in a concentric circles around and is coupled to with probes at the left end. But there's an electric field inside the cavity too, which runs the length of the cavity, and you can couple to it by sticking probes in straight into the cavity from the ends like that, and it will couple just as well. And cavity built in this form will work just as well as cavities work. This is called probe coupling instead of loop coupling. It works just as well. Both forms of cavities are used, although the loop coupling is much more common. They're easier to adjust. That's why. Here you can see a couple of capacitive probes in a cavity. The one on the right is a commercial probe that goes into a cavity, a capacitive probe, and on the left is a drafting of a home-built cavity where the capacitive probes are brought in through the side, which is fine. That'll work just as well. Probes themselves or along the cavity, coupling to the electric field. So these are capacitive coupling probes. Either work just as well, although loop coupling is preferred. There's a third form which hams rarely ever run into, unless they get into receivers. Sometimes cavities are used in receivers, called port coupling. Here you see a 4-cavity system made out of square cavities. And there's the quarter wavelength center conductor inside of 4 square cavities. But the coupling between the cavities is not by probes or by loops. It's by a hole or a port called port coupling. You can just cut a hole in the side of the cavities and you can couple 2 cavities together that way. This, of course, is not adjustable. It has to be built this way. So it's not very adaptable to building ham repeaters, but thought I'd show it since it's a common method. Okay, now we have to take these cavities that we've seen now, these quarter wavelength loop coupled or probe coupled cavities. We now have to make them into bandpass or band reject or notch cavities so we can use them in a duplexer. How do we do that? Well, here's one of the ways. Here's how we make bandpass cavities out of them. We put 2 loops or 2 probes into the cavity, and you notice the probe. I've got the probe one on the right upside down. The center conductors from the bottom up and on the probe coupled one. Here's how you make a bandpass cavity: 2 probes coming in or two loops coming in. Again, the one on the left is the common form in duplexers. it's much easier to adjust those loops than it is to adjust the probes. Now, if we want to make a notch cavity out of the same devices, we have to hook them up differently. Because notch cavities don't go inline. You notice the one before, these here, the energy passes through the cavity, it's inline. But the notch cavities are in parallel with the line. So the energy intercept the energy coming from the inside the duplexer. They intercept the energy in parallel. In other words, they suck out information from what's passing by. And it can be done, as I just see on the left and on the right, with a single loop or a single probe that's hooked across in parallel across the passing line. And those cavities suck out the energy to which they are tuned to. So they're band reject cavities. You can play with and tune band reject cavities, which happens in all duplexers, by adding a little coil or a little capacitor and using two loops in the cavity or two probes in the cavity, and you can create band reject cavities. By doing this, you can really tailor the response of the band reject cavity so the good part of it sits right on what you want to pass, and the part you want to suck out sits right on the part you want to get rid of. It's fairly easy to tune them up, as I've done by building my own cavities. Okay, how do you tune cavities, and how do you tune duplexers? Let's get through this quickly because this is a moderately long presentation. We'll keep it short. Here's a duplexer, a 6-cavity duplexer, typical 6-cavity duplexers, hooked up one side to the transmitter, one side to the receiver, and the central port to the antenna. The first thing we do in a duplexer is we want to put a bandpass cavity right at in the receiver side to get rid of anything coming into the receiver except what's in the band we want to operate on. So this, if it's a 2-meter repeater, this bandpass cavity would be tuned right in the middle of the 2-meter band. And then after we do that, we then want to get rid of what in repeater world is called desense. Desense is the squashing of the sensitivity of the receiver by the transmitter in the repeater. That's desense. And we do that with the notch cavities. The notch cavities, you can see here now, normally we use 2 of them because we on both sides. The notch cavities on the transmitter side are tuned to the receiver's frequency. Well, it's pretty obvious why. We don't want the transmitter to be producing any energy possible at all on the receiver's frequency, thereby desensing it or squashing its sensitivity or making it insensitive. So the notch filters in the transmitter cavities, transmitter notches, are tuned to the receiver frequency. On the other side, the receiver side, we also use notch cavities because we need as much to get rid of the transmitter out of the receiver is a big job, as we've seen. We tune the notch cavities in the duplexer to the transmitter's frequency, so that if the transmitter is producing any energy on the receiver frequency, we suppress it as much as possible, so that between the transmitter and the receiver, there's approximately 120 dB difference in signal level by the time the transmitter's energy gets over to the receiver, which is down by 1,000 million times the power. That's a lot, but we have to do that. Typical duplexer has to have 120 dB of desense rejection. Then finally, to be a good neighbor, we put a bandpass cavity on the transmitter so that out of our antenna only comes energy in the band we're working on. So if there's a local sheriff's department repeater in the same building, we don't blow it away with our transmitter. We don't desense our neighbors. So there's the complement of the way the cavities are tuned up in a repeater. Bandpass tuned to the repeater and transmitter frequency on the repeater and transmit side, and notch tuned to the opposite on the opposite side to keep the transmitter from desensing the receiver. Now, how do you actually tune the cavities? Well, most commercial cavities are tuned as you see on the left. There's the central conductor, which is what determines the frequency of the cavity, is adjustable in length. It's a plunger that slides up and down between fingers, and it's driven by a threaded rod made out of a material called Invar. Invar is a metal that has almost no shrinkage with temperature, so that you can put it on frequency and it'll stay there and won't change frequency when the duplexer gets hot or cools off. So that's the common commercial way. And if you buy a commercial duplexer, it'll have this plunger arrangement in it with an Invar rod in it, which you can retune probably to ham bands if you want to buy a commercial duplexer and retune it. It'll look like this. If you want to build your own cavities, you don't need to bother with this complex method. Just do what you do on the right there. I'm showing probes, but it can be loops as well. Just build the center conductor fixed and bring a bolt in through the end. And you can stick that bolt in through a screw on the end of the cavity and stick it all the way into the inside of the center conductor, or just near it, depending upon how long you make the inner. And you can tune that, that center conductor by capacitive coupling. In other words, you're just adding capacity to the end of it. You don't have to change the length of the center conductor if you're building your own cavities. This bolt tuning method works great. Use an end screw for home-built cavities. Okay, how do you tune them up? Well, here's the two ways you tune them up. You actually adjust them onto the frequency. The old way, which I did for years when I was building duplexers, I used this method. You just use a little transmitter, a handy talkie, and a watt meter, my Bird 43 watt meter, and a dummy load. And I just put power into it, and I keep changing the frequency of the transmitter and writing down how much power came out the other side. And I was easily able to get a picture. It took a lot of time to do it, but I was easily able to get a picture of what the bandpass or the notch cavity looked like. The easier way now that VNAs are readily available, probably a lot of you own the little nano VNAs. They're a great tool to use with building duplexers, because you can hook them up in S21 mode and just read out and just get a nice graph drawn on your computer screen, and you can adjust the cavities very easily. So VNA is the best way. When I was doing cavities, I was able to borrow a spectrum analyzer with a tracking generator, which did the same thing. But the little modern VNAs, the nano VNAs, are a great tool to tune up duplexers. All right, let me give you a homebrew example quickly. Here's the cavity I'm most proud of. This is a home-built cavity for 2 meters, which is built out of commercial cake pans. You can buy them at commercial, restaurant supplies, or often craft centers will have these. And there's the coupling loops that I use, made out of 1/4-inch copper tubing, being fed with BNC connectors. And the center conductor is a piece of copper tubing with an end cap, all screwed to the one end of the cake pans. Cake pans are nice because they're round. They have straight edges like that, and you can couple 2 of them together with aluminum flashing, which you can buy down at your local hardware store. And you can hold the flashing on with typical stainless steel hose clamps. You might have to use 2 or 3 of them in series to get around the cavity. This, by the way, is a 10-inch cavity, and the interconductor is a piece of 3-inch copper tubing, 19 inches long for 2 meters. And there's one of the kind of hose clamps, common stainless hose clamps. You may need several of them. And by the way, if you're ever building a cavity, the correct ratio from inside to outside, the best ratio is 3.6 to 1. That's where the cavity is most efficient. So a piece of 3-inch copper tubing inside of a 10-inch pie pan made it pretty close to 3.6 to 1. Made a great cavity. which worked well as both bandpass and as band reject. I put some capacitors on the outside. And here's the tuning screw coming in through the bottom. That cut a little piece of aluminum plate there and screwed it onto the bottom and threaded it so I could run the screw in through the end. And the top end of the center conductor, I just cut a piece of little piece off the end of another piece of 3-inch tubing, made a slot in it, spread it out so that I can use that to get it initially where I wanted to. So you don't have to use plungers or fingers or anything else to build homebrew cavities. Here's one of the cake pans, which you can buy on Amazon. This is a 6-incher, which would make a great UHF cavity. And here's some of the aluminum flashing, which you can buy on Amazon, or you can, most hardware stores have it. Often you can buy just the piece size you need. This would make a size for a UHF cavity. You'd need about a 24-inch piece for a 2-meter cavity. And of course, the sheet metal screws. The last thing I want to talk about, though, and this is a question that I get asked very often. How do you figure out if you buy yourself an old commercial duplexer, let's say is on 170 megahertz or something, which you might have gotten at a swap meet and you want to put it down on 2 meters? You can't use the wire or the cables that connect the two because they were cut for high band or for higher in frequency. How do you change the length of the cables between the cavities to make them right for 2 meters if you're trying to tune an old high band duplexer that you bought at the swap meet, which is for 50 megahertz higher? How do you, because the little plunger inside will probably tune to 2 meters, but the intercables between the cavities are the wrong length. How do you figure them out? Well, it's not that hard. Here's the way. Here's a coax between 2 cavities. I learned earlier on that it's easy to determine the length of that. There's no formula, though, to calculate it. So if you're trying to make a duplexer out of an old commercial duplexer, you can't just figure the length of the coax, with some equation. There isn't an equation for it because it's a very complex issue, but not in theory. In theory, the total length of the dotted line is exactly half a wavelength. Why? What happens at the ends of a piece of half wavelength of coax? It simply repeats whatever's at one end at the other. What the cavities want to be is they want to look like they're connected directly to each other. And you do that by hooking them together with a half wavelength of transmission line plus the loops. Not just the line is half a wavelength, but it's the loop, the line, and the loop that's a half wavelength long. The total dotted line is half a wavelength. Well, that's very difficult to figure out because the coax has velocity factor. The loops don't have velocity factor. How do you calculate the length? Well, you don't. You just measure it. It's much easier. The way I did it, I made up myself a whole bunch of little jumper cables. I was doing all my cavities in RG58 in those days, which will handle 50 watts rather nicely because all my repeaters were 50 watts or less. And I made up a whole bunch of little jumper cables in 1-inch increments and all had BNC connectors on the end of it. Then all I did was hooked up my vector network analyzer or my spectrum analyzer, which I was using at the time, tracking generator, did the same thing as a VNA. And I simply put on one of these and I had to look at the bandpass. That's what it was. If it wasn't right, I put another one. And I kept changing these little half wavelengths or little short lengths of coax until I got one that was the right length. It gave me the bump and the dip where I wanted it. Piece of cake. I didn't have to figure out. But what I was doing was essentially pragmatically determining what the exact half wavelength was from the grounding end of the loop, through the loop, up through the piece of coax, back down to the other cavity, through the loop, back down to the other grounding end. That was exactly half a wavelength when I got my bandpass or my band reject the way I wanted it. It was easy to do. And this is the way you convert old cavities. Don't try to figure out the length of the coax. Okay, lastly, and this is just 2 slides, and we'll end this. There's a cousin to the duplexer, which you probably should be aware of because sometimes you run into them in high quality commercial receivers. It's called the helical resonator. Although you can use the principle to make cavities, I've done it. There's a cavity on the left, a typical bottle, as we call it, quarter wavelength coaxial cavity. You don't have to make the center conductor, though, a single straight piece of conductor, as I show it there. You can make it into a coil, like you see on the right. That coil has the same electrical wavelength as that straight piece on the left. Therefore, you can reduce the length of the cavity very significantly by making the center conductor into a coil. Or you can use a combination of the two. And that's what I've done in duplexes. I use that same mechanical structure that I showed you for the 2-meter cavity, but I replaced the center conductor with a piece of copper pipe, half the length, and the other half of the length was a coil of 1/2-inch copper tubing. And I was able to get that same 20-inch piece of, that same 20-inch length of that cavity to work on 6 meters. And I built a perfect 6-meter duplexer in what I called the heliplexer. It was the center conductor was half pipe, half coil, and it worked just great on 6 meters. But it was only about 2 feet tall, the same size as a 2-meter duplexer. I never got around to building a 10-meter one, although I did build a 10-meter duplexer for the Stanford Linear Accelerator Group out of some 6-foot tall bottles that they happen to have. Here, by the way, is a helical resonator. This is the front end of a very expensive commercial VHF receiver. You can see the whole center conductor is not a quarter wavelength long. It's electrically a quarter wavelength long by making it out of coil. And in this case, the cavities are coupled together by ports. And here's a homebrew version that I took a picture of somebody off the line who was also using helical resonators in the cavities. They work quite well. They're sharper, of course. Anytime you make something smaller, it gets sharper, but it certainly can make good duplexers with them. So if you'd like to read my book, there it is again. I put the direct link up to it. It's on my website for you to download. Just go up to W6NBC.com and /articles/duplexer.pdf, and you'll download the whole book. And if you haven't read it and you're interested in building duplexers, or you'd like to see all of this stuff repeated, it's all in the same book. And there's the QR code if you'd like to snap a picture of it. And that's cavity duplexer. Sorry if this has gone a little bit too long, but it's a big topic. But no longer is it a mystery. They all work by known principles.